session. So in this session, we'll discuss about the IIR filter design from analog filter, Chebyshev, Chebyshev filter, Chebyshev filter. Okay. So only here we'll take one problem. Depending upon the specification, we can choose the formulas and we can determine the number order of the filter. So the Chebyshev design determine the order. Okay. For the given specification is zero point 0.9 h of e power j omega from 0.9 to 1, where omega is 0 to 0.25 pi, and h of e power j omega for less than 0.24, the stop band is given. So omega 0.5 pi to less than or equal to pi. So you realize the system direct from two structure. Okay, I'll give you only the steps how to design a filter. Okay, what are the steps you have to follow for designing the filter? You practice and compute the values each and every step, and you can cross check. So from the given specification, this is you can choose one of the formulas with respect to the pass band gain. This is your stop band gain. Okay, this is your omega s radians per sample, and this is your omega p is the radians per sample. So you know for a okay, for impulse invariant method, use impulse invariant method. Impulse invariant method. So in that case, omega s equal to omega p by t, and omega p is equal to omega. So this is omega s, omega p. This is omega p equal to omega p by t, omega s equal to omega s by t. So for impulse invariant method, so omega p is equal to 0.25 pi by t is equal to 1. Take t is equal to 1 second. So 0.25 by t, which is equal to 0.7854 radians per second, and omega s, which is equal to omega s by t, which is equal to 0.5 pi by t, which is equal to 1.570 t 08 radians per second. So from the given specification, so you can first step is determine the order of the filter. So from the given specification AP and AS, you can choose this formula cos H inverse of 1 by the gain in stop band minus 1 divided by 1 by gain in pass band minus 1 to the power half divided by cos H inverse omega s by omega p. So substitute all the values of AS, AP, omega s, omega p, then compute the value of n and cross check 1.077. So n is approximately equal to 3. Once if you determine the order of the filter, then poles, once n is known, you can find out the Butterworth poles. Once n is known, determine the Butterworth poles. So determination of Butterworth poles, out then n is odd and even. So for n is odd and even in pi, k is equal to determination of angle of the poles which is equal to n is so pi of k is equal to if n is odd, no, so odd means k pi by n, where n is equal to odd and k is equal to 0 1 2 n minus 1. So k equal to 0 1 2 into n 6 minus 1 3, so 2 3 4 5. So you determine pi 0, pi 1, only steps I'm saying, pi 1, pi 2, pi 3, pi 4, pi 5. So butterworth poles, then find out the stable poles. Stable poles for transfer function should be stable, should be for transfer function for stability. Per stability, stable poles are between 90° and 270°. So this only will be considered as stable poles. Then once if you determine the butterworth poles, then translate butterworth poles into poles, translate into chebyshev poles. Chebyshev poles. So the chebyshev poles take butterworth poles. Okay, take butterworth poles. Then the design parameter A you have to determine. Okay, the design parameter A butterworth poles. So that is A is equal to 1 by n sine h inverse 1 by epsilon. Butterworth poles, for example, what are the poles? B1. Okay, how many poles for stable that you have to consider? B1, B2, B3, B4 like that. So B1 for example A plus JB and B2 is A minus JB. So what are the butterworth poles you determine? Example I'm saying B1, B2. Then design parameter A to determine. Then find tan HA and cos HA. Then fourth one is normalization you have to do. So normalization you have to do. So the new post B1 dash, B2 dash. So multiplying by tan HA, multiply by tan HA. Then determine the denormalization. For denormalization, multiply by the C1 pole, C2, C3, C4. So that poles have to multiply. So for that multiply by cos H function, cos HA. So cos HA of the B1 dash, B2 dash, B1 dash and B2 dash. So you have to determine the poles. Once the poles are determined, the analog transfer function is can be written as P by S plus C1 into S plus C2 into S plus C3. Okay, so the P is equal to the C1, C2 and C3. So once you determine the order, then determine the poles and translate the poles, then H of S, find the analog transfer function, then apply the partial fraction method, find the coefficients, and normalization you have to do. This is normalized transfer function. For denormalization, put S is equal to S by omega C for denormalization. Okay, for denormalization, this is a normalized transfer function. Normalized transfer function. Then this is a denormalization. The denormalization is nothing but convert this normalized transfer function into prototype into the low pass filter. For example, the low pass filter. If you want to design, so put S is equal to put S is equal to S by omega C and find omega C. So in that impulse movement omega C equal to omega P, which is equal to 0.7854 radians per second. So impulse invariant method we are using. Then substitute this. Then you find the transfer function H of S. So this H of S Okay, h of s is equal to, you can cross check the values. 5 numerical values, I'll give it here. S cube plus 1.0214 s squared plus 1.2761 s plus 0.5162. After applying, put s is equal to s by omega c. Then h of s, which is equal to 0.2501. You can cross check the steps. S cube plus 0.8022 s squared plus 0.7844 s plus 0.2501. So then you apply the partial fraction and find the coefficients. Then convert this h of s into h of z by using either bilinear transformation or impulse invariant method. So finally h of z is equal to 0.0906 z inverse plus 0.0698 z minus 2 divided by 1 minus 1.8516 z inverse plus 1.461 z minus 2 minus 0.4484 z minus 3. Now the order is 3, so 3 delay elements are required to realize the system. The final step is realization. Platform 2. So 3 delay units are required. 3 delay units are required. So 3 delay units. Z inverse, Z inverse, Z inverse. So what are the coefficients? Pole coefficients. So the pole coefficients are 1, the other one is 1.851, the other one is minus 1.461, then last one is 0.4484. So this is the realization part of a direct 2. So here the coefficients are 0.0966 and 0.0698. This is y of z. So this is the direct realization. Okay, so this is the okay. So the various steps how to design chebyshev filters given. So you can practice the problems, more problems from the brackets and opening and non-opening. So here only we briefly explained how to design chebyshev filter from the given specification. First, determination of order of the filter. Then once order of the filter, if you know how to translate the determination of Butterworth poles, then how to translate the Butterworth poles into Chebyshev poles. Only for stable poles we to consider. Then the Chebyshev design Butterworth poles. Then design parameter A, tan H, A, cos H to calculate. Then normalization and denormalization of the poles by multiplying tan H and cos H. Then the normalized transfer function to determine. Then denormalization for low pass filter, put S equal S by omega C. Then the computation results I specified here. You can cross check. You can compute all step by step and cross check whether you got the same results or not. Then convert h of z into h of s into h of z by using either this is by bilinear transformation or impulse limit method. In impulse limit method, okay, then realization of the filters. Okay, so with this we can conclude this session. So last video I have started this session, but it is not recorded. So that I will record it again.